Hello, my name is Fabio. I studied physics at the University of São Paulo here in Brazil, and I have a nickname in the internet where I wrote lots of theories, hypotheses about Stanley Meyer work, and it's Sebos Fato, the nickname, is the name of this channel, and I invite you to like this video and to follow the channel so you can get news when we post new videos. So let's start. We are going to start talking about the DC power supply we are building and how we are building, what's the diagram, and a little bit of the technology behind it, and a little bit of the theory behind, so everyone can understand what we are talking about. Okay, so DC power supply. Okay, I'm gonna start with the plug. Okay, then I'm gonna have a circuit breaker about 30 amps, and it works as a switch as well. This is going to be connected to a transformer, a 6 kilowatt transformer. This is 240 volts RMS. Okay, 240 volts. And after this transformer, I'm gonna have a dimmer that is connected like this. Okay, this is a cone, and after this I'm going to have a switch here and a three-phase DC powered full wave bridge rectifier. Okay, this is a positive, negative output. After this, we're going to have a capacitor, 1.5 millifarad capacitor, 450 volts. And to keep it simple, it should be like that, but we're actually going to place a little bit complication here. We are going to add a small choke here in this configuration, and this is it. This is the positive output here. Okay, so this switch is going to make possible to make it 110 volts or 240 volts, because this center tap is connected to one of the phases of the three-phase rectifier, and this dimmer has this COM input. So when we switch off this phase, we are going to stick with the other phase here only. So it's going to take only 110 volts out of the transformer. And it's still going to vary from 20 volts because it's peculiar of the construction of this dimmer. Okay, after that we are going to have the transformer, and for the transformer we're going to have this positive here, the same here. After that we're going to have a diode. Okay, and then this is the primary of the transformer. Then we have the IGBT here, a MOSFET, whatever, and we are going to have a system here in such a way that we can make it regenerative feedback, such that this primary can collapse very fast. And not only that, you can get a burst of voltage spike when the switch starts again. I'm going to explain here right now. Here we are going to place a capacitor. Okay, this capacitor is going to charge when the switch open. This coil is going to charge this capacitor in this direction. Okay, and then we are going to have another coil here too, connected to ground. That is a 5-to-1 ratio to this primary coil. We call this clamp coil. This is the primary coil, L1. Okay, and P1, D1, D2, D3, and there is a diode here. We're going to use the diode from the GBT, but there's D4 here too. Okay, this is the whole circuit, and what happens is this this clamp coil has 5 times less turns than the primary coil. So when the switch opens here, we are going to have let's say 240 volts. Okay, it's not going to be exactly that, but we are going to have 240 volts, and this is connected to the capacitor. Okay, so it's going to stick to this voltage, limiting the maximum voltage this is going to arrive here. So part of the energy just come back to the capacitor right here, and some of the energy is going to charge this capacitor up to this ratio of voltage we chosen here. But to calculate that, we need to make some formulas, some arrangements, so we can understand what we are going to do. So if this is 1 to 5, and here we have 240 volts, and this is 1 to 5, this tells me that the maximum voltage when this switch opens is going to be 5 times that. So it's going to be 1000, let's round it to 150 volts. Okay, so this is this is going to be the voltage across the coil. Okay, across the L1. The voltage at this point is going to be that voltage plus that voltage, so it's going to be roughly 1500 volts right here. So across the capacitor we have this voltage, 1250 volts. Okay, so when this switch turns on again, that voltage is going to appear across this clamp coil that is going to act as a kind of a primary for just a little bit of time, because it's going to be very short time of this capacitor discharging into this very short coil, and this is going to make this voltage to appear in that direction. So it's going to be a positive here, and this voltage is going to be 1205 volts times 5, so it's going to be like 6000 volts or so. Okay, so how do we know what kind of capacitor, what kind of voltage, how we can manage this voltage, how we choose these components? Okay, let's calculate it. First of all, I'm going to give you, this is going to be 100 volts, actually 100 amps diode, and 400 volts. Move of this. This is going to be over 2000 volts diode. Also, this capacitor is going to be over 2000 volts, so it can work safely. This is going to be a 1600 volts IGBT. Okay, and so let's get to the calculation. We know that energy in a capacitor is equal to the voltage squared times C over 2. Also, similarly, the energy of the inductor is equal to the amps squared times L over 2. And we know that the voltage, if we want to know the voltage of a capacitor, we need to know the energy of the coil. So the voltage of the capacitor is going to be equal to the square root of 2 times the energy of the capacitor of the inductor over C. Okay, so that leads to that voltage equals to square root of 2 times I squared times L over 2. Okay, substituting this with this, we get that 2 cuts with 2, and actually there is a C2 here, and we get that we can make this square root split to cut this with the square root and leave the square root right here. So we get that the voltage across the capacitor must be the current on the inductor, okay, times the square root or L over C, right? So how do we choose the C so that we know the L, but we need to know what kind of, when we build the transformer, we know the inductance, okay? So we need to choose the capacitor. So how do we choose the capacitor? We have to make this equation easier to solve. We actually make this by making the square roots disappearing. We can make this by elevating everything to the square. So we put everything in the square, this cancel out, and we have that V, actually let's make it once. C is going to be I squared over V squared times L. So with that equation, it's easier to find the capacitance based on the amps you're expecting to have here, and the inductance that you already know because you built it. And the voltage is going to be that voltage you limited here. So you have this maximum voltage, so you choose the capacitor. Okay, so you have the voltage, you have the inductance, you have the current, so you just need to know the capacitance. And there's something interesting here, that if you think about it, voltage over the capacitor is going to actually be the current, the amps, times the square root of L over C, actually is Z. So that's really interesting that the Z that's have nothing to do with the time. It has to do with the energy. It has to do with the energy among the components and not with the time constant or the frequency or whatever. And that's it for now. I hope you enjoy it. And please like the video, comment below, share with your friends, the family, join the channel, okay, follow us for more. And if you want to have more detailed information, you can ask us for the private group where you can contribute more donations, and we are going to share a little bit more about this we are doing, how we are doing, the pieces we are using. So if you want, you can even make it the same, or you just don't make the same. You use this, let's say, information to go further or to save money, okay? So thank you for your time. Good luck. Bye-bye.